apparently someone wants a picture with a blog hash. Was that block number correct? If it's not, you can't go to any future meetups.
Okay, guys, we are good. We are good. Coming through. Excuse me. Excuse me.
Okay.
All right. Sorry. Okay, it's been a very crazy half an hour. Right now, the live stream is up, so I hope we are good to go from now. All right. Okay, hello. Good evening, everyone. Good evening, SG Innovate, ladies and gentlemen, partners, friends, guests. You guys amaze me, man. This sign-up is faster than ICO. I cannot imagine, like, this kind of sign-up is just insane. And I believe that in some way it might have frustrated some of you folks not coming in. I hope you guys try to understand that we try to get you guys the best venue in Singapore, and we will always try to do so. So bear with us while we try to get a bigger venue in the future. Yeah. So we started this group 2.5 years ago. 0 people. Today, it's about 2,600 people. We are the largest in Asia, 4th in the world, almost catching up with Silicon Valley. So give yourselves a pat on the back. Celebrate with some wine. Thank you. We have 4 to 5 events lined up for August and September. We have Swarm coming in next week, which is part of the Ethereum Foundation. The team from Chennai will be speaking on that. We have Ray Dow, a real estate investments on the Ethereum blockchain, will be speaking again. Macenas, an art piece on the blockchain, is something interesting you should look out for as well, all happening in August and September. So first and foremost, before I invite Vitalik to speak, I have a very short message from the venue sponsor, Howdy. Please.
Hi everyone, I'm Andy from Howdy, and we're really excited to have partnered with SG Innovate, as well as DG and the brilliant Vitalik here this evening for the Ethereum event. As a lot of you are very well aware, networking at times is fundamentally difficult, particularly in a room like this. We've got 200, 250 people. You might chat to the person next to you, or you'll just simply hand out vast numbers of business cards, which is completely inefficient. So what we've done with Howdy, it allows you to discover, connect, and collaborate with everyone in the room here this evening. And as a lot of you are very well aware, there's some very important and interesting people here that you want to meet, and which you are able to do on Howdy. So if you haven't already, download Howdy, get connecting, enjoy the evening. Looking forward to it. Thank you very much.
Right, so before we begin this talk, the room might be a little warm because Ethereum itself is really hot right now. So let's welcome Vitalik Buterin to Singapore.
Guys up there on the second floor, can you actually hear me? Wave if you can. Thumbs up is not a wave, so they can't. Okay, great. So this is definitely by far the biggest meetup I've ever had in Singapore, and I think it's probably actually one of the 3 biggest I've had in the world. I remember there was one in London that went up to 220 to 250, and one in Shenzhen in China about 3 weeks ago that also broke over 200. So I don't think there were ever any that broke 300. So yeah, I mean, congratulations, Singapore. Also, big congratulations on very creative use of space with the staircase there. No, this is actually a really nice setup. You can actually fit quite a lot of people in. You just maybe want to put like 20 more VIP seats up on there. No. Yeah, okay, so the topic that I have been told to present about is basically to give a general update of where Ethereum is, ongoing progress with things like Metropolis, ongoing progress with Casper, ongoing progress with Sharding, and I will spend some time talking about each of those things, but also, because this is a meetup and I don't want this to be just myself talking at people about things that they may or may not understand. I'd also welcome questions at every step of the way, and I'm happy to generally answer anything that people are interested in asking about, with the exceptions of future price predictions of Ether or Ethereum-based tokens. If you want to ask about future price predictions of the euro to US dollar exchange rate, I can answer that, but I don't think my opinion is very useful. So, first of all, how many people here know what Casper is? Okay, how many people know what the revert opcode is? Metropolis. Ethereum. The word horse. That last one was a control. I'm very disappointed that so few people know what horses are. So, okay, now that's definitely helpful. So, for how many people is this their first Ethereum meetup? Okay, quite a lot. So, I'll probably just start off by giving a kind of 1 to 2 minute introduction into what Ethereum is for the benefit of those who are fairly new here. So the basic idea behind Ethereum is that it is a general purpose blockchain, just to put it in very simple terms. So a blockchain is, as I like to describe it, a kind of decentralized computer network that contains some kind of memory, right? And the reason why I use this definition is because I think it captures the kind of two elements that make a blockchain important, right? So before we had blockchains, we've had decentralized networks for over 20 years. So how many people here have used BitTorrent? Every single one of you, presumably, downloading legal stuff. And how many people here have used some form of centralized online payments or online banking before Bitcoin existed? There we go. So decentralized networks existed before blockchains existed. And also the idea of systems that had some kind of memory in them existed before blockchains existed. What blockchains do is they basically bring together those two properties. Now, why are those two properties so important? So first of all, decentralization is important for reasons that hopefully people here already appreciate. So the idea is that we can build systems, networks, protocols, institutions that are fully open, fully public, where anyone can participate, and where there is no single party that is privileged over every other party, and where there is no single party that you have to trust in order to trust that the network will keep on working. So it is a protocol where the story for why you should trust that protocol does not have to do with an already existing assumption that you trust any specific person. Now, this is in the real world, there are lots of situations where we already trust people. So for many things, we trust the companies we work for many things, we trust our governments, for many things, we trust Google, Facebook, Twitter. But first of all, even in those cases, there are opportunities to build applications that do the same things that exist now, but that don't require you to trust as much. And second of all, if you want to build applications that are really global and that cross organizational national boundaries, and where the participants can be as small or as large, anyone from the richest or the poorest country, then you want to build systems that don't depend on the assumptions of trust in the same way. That's decentralization. Now, second thing is, why is memory important? So I'll repeat the story that I tend to give in these situations quite a few times, and the story is this. In networks like BitTorrent, let's say I have a file. Let's say I have some new book, and I want to send a copy of this book to one friend. I make that transaction. I send this book. This is a transaction that only myself and the person I am sending to have to care about. No one else even knows that this transaction exists. Now, here's the problem with applying this sort of thing to money. Let's say that I have 100 digital Singapore dollars, and I send these 100 digital Singapore dollars to a friend. Now, let's say then I create another transaction that looks exactly like the first transaction, and this second transaction broadcasts a copy of the exact same 100 Singapore dollars to another friend. I broadcast both of these transactions. Yay, I have converted $100 into $200. We are rich, we have communism. basic income for everyone. Of course, in reality, if money worked this way, the Singapore dollar would hyperinflate faster than Zimbabwe. And as I've been led to understand, the Singaporean government cares about economic stability. Any Singapore government people want to confirm that? Okay, so if you want to have a system of transactions of money or any kind of digital value, money is an inherently social thing to a greater extent, to an extent that simple messages are not. When I send 100 digital Singapore dollars to you, that is not something that just myself and the recipient have to care about. The fact of that transaction is also a fact which is of concern to any other person in the entire community that uses that currency that might end up receiving those digital dollars in the future. Anyone else in this community needs to know that I no longer have these units of money and that the recipient now does have these units of money. So this is why currency needs some form of memory. Currency is not the only application that requires some form of memory. So the other one I typically go through is domain name registries, right? So the kinds of systems that you use to register websites, you know. So for example, let's say I want to register ethereum.org, the domain name. And what would I do? Well, I would go through this domain name registration process and I would send a few messages that say, I want to register this website. But then what if 3 years later, Ethereum gets big and some other less scrupulous and less honest guy decides, I want to register ethereum.org too. And so what the second guy does is he would go through the exact same sequence of steps that I went through in order to register ethereum.org, and he would try to register the exact same website himself. Now, clearly, if we had a domain name system where the second guy could succeed, it would be a complete failure because, you know, anytime a company got big, anyone could just freely impersonate them, and yay, here we have Microsoft.com. Please enter your private key and get a free Xbox. So, if we want to have a stable online economy, then we need to have this kind of notion of persistent identifiers, and we need to have some way of not having this kind of problem. And so there's an obvious solution. When you have two people who both registered the same domain, generally you want the first one to succeed and the second one to fail. But now you have to have a notion of who is first and who is second. And so you need some notion of memory, right? So this is the idea of why memory is important. So we know why decentralization is important. We know why some notion of memory is important for many applications. If you have applications where you want decentralization and where you want memory, you want a blockchain. So now, why Ethereum, right? So blockchains existed for quite a while before Ethereum. There were systems like Bitcoin, which did a peer-to-peer digital currency. There were systems like Namecoin, which did a peer-to-peer decentralized domain name system. But then people started realizing maybe there's other things that you might want blockchains for. Maybe there's other applications where you care about decentralization and where you care about having a memory. You might want to use these systems to register other types of digital assets. You might want to use them for to exchange digital assets. You might want to use them for contracts, smart contracts, legal agreements, financial contracts. You might want to use them for crowdfunding. You might want to use them as title registries. And the number of use cases started increasing. And so it started to become obvious that it doesn't make sense to have one blockchain for every single type of application, and it doesn't even make sense to have one blockchain for 10 types of applications. What you instead want is to have one platform where this platform understands a general purpose programming language, where if you want to build any kind of application, you would encode the rules of this application in a computer program, upload this computer program to the blockchain, and then any user in the world can interact with this particular application by sending transactions that say, this is a transaction that wants to interact with this particular application that exists at this address. And so you can have applications of very many different types, many industries, many use cases live on the same platform, and the complexity of building your own thing that requires decentralization and memory goes down from the complexity of building an entire network from scratch to the complexity of writing a computer program and clicking upload. So how many people here learned something from that explanation? Well, how many people here learned something from that explanation who have known about Ethereum for the last 2 years? Cool. Okay. So, no, that's always good to know that it's helpful. So that's kind of where the vision started, right? And the vision has probably evolved quite a bit over the last few years. So, for example, when we started off, it was mostly just about programmable money. The idea is, we have this idea of peer-to-peer digital cash. We can have a programming language, and, well, we can stick this programming language and money together, and we can create money which is controlled by computer programs. So there was an idea that was created in 1995 by Nick Szabo called smart contracts. And the analogy that he used to describe the concept is this. Think about a vending machine. A vending machine is basically a physical hardware device which enforces a particular set of rules. And the rules are simple. You put money in, water comes out. You do not put money in, water does not come out. Now, what the purpose of this physical device is to enforce this kind of set of conditions and do so in a way that requires nothing but a mechanical contraption. Now, of course, if you really try hard, then you can break the vending machine. If the vending machine is designed incorrectly, and if the vending machine has a bug in it, then maybe you can put a bit of money in and 3 bottles of water come out. And that's what you get if there's a broken vending machine. And if it's a physical vending machine, code is law. 3 bottles of water come out. So the idea behind smart contracts is that to try to take this this idea of using physical hardware as a way of more cheaply enforcing kind of conditional agreements and bring it to the digital world. The main benefit of the digital world is, unlike the physical world, where security is expensive, where defense is expensive, and where attack is cheap, where a $10,000 gasoline bomb can destroy a $10 million building, in the digital world, it is defense that is cheap and it is attack that is expensive. A message which is encrypted with a private key that costs 1 millisecond on a computer to generate will take trillions of years for even the NSA to decrypt. So that's the digital world. So what can we do with this? Well, we can use the benefits of the digital world to create much more powerful digital lockboxes, and we can try to use them to enforce these kinds of conditional agreements. Now, in order for this idea to work, there's a problem. You need to have some notion of digital cash. And furthermore, if you want the lock to really be trustless, you need some notion of digital cash where the digital cash itself is trustless. And so the idea is that now we have blockchains, and blockchains give us this form of money which is natively digital, where the digital thing itself has value, without reference to any particular thing in the physical world. So now we have a form of value which is natively decentralized and natively digital, and we can create computer programs. And we can create systems where the digital money itself can belong to computer programs. And the computer programs might have conditions. They might say, if you give me a solution to this math problem, then you get a digital dollar. If you do not give me a solution to this math problem, then you do not get a digital dollar. And so you can basically automate half the job of a math professor. That was a joke. So that was the kind of one of the original use cases that probably motivated at least a lot of the interest in smart contracts and general purpose blockchains as well. And the reason why general purpose blockchains are such a good fit is because if you have a general purpose programming language, then you can write smart contracts basically with any kind of conditions you want. You can use them to represent bounties for math problems, bounties for computational tasks, escrow agreements, financial agreements, like insurance systems, potentially things like decentralized autonomous organizations, lots and lots of different things. So that was the first use case. But then we started to realize that general purpose blockchains are not just about general purpose smart contracts controlling digital cash. General purpose blockchains are useful for any kind of application that benefits from decentralization and that benefits from having some notion of memory. So the number of applications that people got interested in started to grow. Probably the first two things that people got excited about in Ethereum were smart contracts and using it as a platform on top of which to build a decentralized domain name system. Now you might wonder, well, we already had a blockchain that would do decentralized domain name systems, and it was called Namecoin, and Namecoin did not really go anywhere. But then part of the reason why Namecoin did not really go anywhere is because there weren't really many things that were attached to it. It was just a system by itself, and there was not much incentive to integrate. If you have a decentralized domain name system that sits inside of Ethereum, and this is an environment where lots of different applications are going to exist, lots of different applications are going to talk to each other, and there's going to be lots of users that already care about using decentralized applications for various purposes. Now you have a stronger network effect, and you have a stronger kind of breeding ground for this kind of application to actually take force. So after this, people continued to get interested in using Ethereum for a lot of these different use cases, many of which had quite little to do with money at all, right? So some of them had to do with decentralized, provable blockchain-based voting. Some of them had to do with things like identity management and supply chain tracking. Some of them had to do with various kinds of digital assets that were not financial, video game tokens. Some of them had to do with just recording information in the blockchain. There's a project that came out a couple of weeks ago called Leroy, which is basically Ethereum-based decentralized Twitter. Now you might think, oh, well, isn't it kind of stupid to stick Twitter messages onto a computing platform where everyone has to store every message forever? Well, in the long term, yes, but for now, it turns out that the transaction fee for sending one of these messages is still less than 1 cent. So there you go. Even if you send 100 messages a day, 1 cent times 100 is $1 a month. Really, such a high price to pay for decentralization, censorship resistance, and a permanent globally accessible log? Maybe not. So once you start creating a general purpose platform, then all of these things can kind of start happening on top of it. And this is what we've seen over the last couple of years. And this is kind of the point where we're at now. We're at this kind of tipping point where the mainstream is starting to realize that, wait, blockchains actually work, and they're actually really cool, and they're actually really useful for these kinds of things. Here's the hard part. Everyone ready for the hard part? Anyone not ready for the hard part? The exit, I believe, is over there. So the hard part is, even though right now adoption is going up and up and up, and interest is going up and up and up, and unfortunately there doesn't seem to be an opportunity to present slides today, but if there was, I had one ready that showed how today and yesterday Ethereum for the first time broke through 400,000 transactions in one single day. It's 5 a second, 40% of Uber. Well, okay, I'm sure the Uber rides are actually much more useful than Leroy messages, but you get the idea. So the difficulty that now remains at this point is basically technology. Right? The fact is, blockchain technology, as it currently stands, is just not good enough in order to fulfill the full vision of decentralized applications with memory for the masses, where the masses are defined as not just millions, but possibly hundreds of millions, and in the long-term future, billions of users. So what are these obstacles? And I can talk about the smaller stuff, So I can talk about things like privacy, I can talk about security, I can talk about usability, I can talk about blockchain security, blockchain efficiency, smart contract auditing, and I will touch on those things later. But probably the biggest one by far is scalability. So here's the problem with blockchain scalability. A blockchain, with the way that it currently works now, is a platform which gets its decentralization from the fact that every single node in the system downloads and processes every single transaction in the system and verifies each and every one of these transactions for itself. Now this means that, first of all, you have a lot of decentralization, and it also means you have a lot of backups. We are very, very far away from ever worrying that any single Ethereum block will ever become fully inaccessible and lost. But the price is efficiency. And here's the best way to think about the price. If every single node in the network has to process every transaction, this means that the network as a whole cannot process more transactions than one single node. This is bad. You cannot have the world economy be processed on one single guy's computer. So we have a problem. Now you might say, oh, well, we have Moore's Law and people's computers get twice as good every 2 years. Up to some point, sure, you can scale blockchains up, you can bump block sizes up, and that works fine. But eventually, you start to realize, oh wait, well, at 12 transactions a second, we have Uber. At 200 transactions a second, we have PayPal. At 2,000 transactions a second, we have Visa. At 80,000 a second, we have the Shanghai Stock Exchange. At 1 million a second, we have the expected 25 billion devices that are expected to be IoT within the next 10 years. So, there's a lot of demand. Current blockchains process, Bitcoin does 3 a second, and Ethereum has now gone up to 5 a second. Now you might say, yay Bitcoin, but which is bigger? The difference between 3 and 5, or the difference between 5 and a million? Who here thinks the difference between 3 and 5 is bigger? Oh wow, 0 people. So, no, it's interesting that there's exactly 0, because there was this article that I read on a blog a few weeks ago that talks about this thing called the lizard man coefficient, which basically suggests that about 4% of people, if you ask them in polls, literally believe lizard men run the world. And apparently about 4% of Obama voters in the US believe Obama is the Antichrist. So there's supposed to be this kind of coefficient of 4 people who answer silly stuff in polls just for the hell of it, but this time we got 0. So, no, please do not buy Neo. Sell your Neo. That's right. OMG, that was brazen. That was brazen. So, okay. Take out your phone, sell your Neo, 30 seconds. Okay, so the 5 in a million is bigger than the difference between 3 and 5 by a lot. So the point of these examples is that getting from the kind of scalability we have now to the scalability that we need in order to achieve decentralization in large portions of the real economy doesn't just require tiny tweaks. It really requires kind of fundamental changes and rethinks and breakthroughs, and very deeply changing the way that blockchains currently work, are designed, and are used. And there are definitely kind of short-term strategies that you can use in order to make existing Ethereum implementations 5 times more efficient, in order to make the protocol 50% more efficient, in order to make people's use of the protocol 2 to 4 times more efficient. And you can get a bit up there, and that might be enough for half a year, or might be enough for a year. But if you want to go further, then you have to kind of break through the fundamental barrier. And I'll talk about probably 2 major techniques. By the way, you should sell some more Neo. Sell some.
Please remove the sign, thank you.
So,
Disclaimer, we do not support anything related to tokens here.
so you should, where was I? So there's probably two major strategies that you can employ in order to kind of really fundamentally change the way that you use your blockchain to make your usage more scalable. And I'll try to explain both of them in a semi-technical way. So the first strategy, and this is a fairly general strategy, is basically this. The only case where you really need a kind of trustless way of getting everyone to agree, of getting consensus on some particular fact is if there actually are people who disagree about that fact. So if there are people who disagree whether this coin belongs to me or this coin belongs to you, or whether some domain name belongs to me or some domain name belongs to you, then we need some form of strong consensus, strong agreement to adjudicate between the two and securely, reliably, and permanently and immutably choose one or the other. In the cases where you don't disagree, in general, there are going to be ways to avoid having to use a blockchain entirely. So I'll give one simple example, and this is a technology called payment channels, and this has existed theoretically at least since around 2012. The concept of payment channels works as follows. Let's suppose that I am an internet service provider, and I am selling you internet service. And let's say we have agreed on a rate of, let's say, 1 cent per megabyte. And let's say that you start using a connection. Here's the naive way to do this. Every time you use a megabyte, you're required to send a blockchain transaction that makes the one payment of 1 cent. And unless you send that transaction, I shut down service. This clearly works. The problem is, though, that if you're going to send a transaction every time you need to spend 1 cent, that your transaction fees are going to be way higher than the amount of money that actually gets sent. So here's what you do instead. When you start your connection, when you kind of sign up as a user, you put, let's say, $100 into something that we will call a channel. So you can think of a channel as being a smart contract. It is a computer program, and the computer program will have certain rules that I will explain later. Then, let's say you then use 1 megabyte. In order to keep using my service, I will then ask you to sign a ticket. I will ask you to sign a digital message. And this digital message now says, I have paid 1 cent. Then, let's say you use another megabyte. I will ask you to sign another digital message. This next digital message says, I have paid 2 cents. Then I will ask you to sign another digital message saying, I have paid 3 cents. Then I have paid 4 cents. I have paid 5 cents. Now, let's suppose that then, in the normal case, eventually, you want to cut your connection and you want to get your money out. Here's what we do. You would submit the last ticket that you sent into the smart contract, and the smart contract would see, oh, this ticket says you have spent $10, and so the contract decides, okay, well, we should now give $10 to me and refund the $90 to you, right? So then you get back your $90, I get my $10, and we go on our merry way. This is the best case. Now, here's the second case. Let us suppose that I go offline. So I just decide I am going to be malicious, or I got hacked, or whatever happens. Then you can still submit the ticket, and your ticket by itself can get you the money back. Now, here we're going to try the third case. The third case is you are malicious. In this case, you are not going to send the last ticket that you signed that says that you paid $10. Instead, you are going to submit the first ticket that you signed that says that you paid 1 cent. So then here is how the smart contract deals with this problem. The smart contract provides a time window. During this time window, I have the ability myself to submit the last ticket that you signed, the ticket that I believe is the highest value ticket, is the ticket that should be the correct one. The smart contract has a rule that says it will accept the highest valued ticket that was submitted during this challenge period. Whatever the highest value ticket is, it accepts as the truth. And so if you try to cheat me, then I will submit my ticket, the contract will adjudicate, and you will still get just $90 back, and I will get the $10 that I deserve. Now, notice that in this kind of scheme, if nobody cheats, then only 2 transactions need to get sent. The first transaction is you joining the channel. The second transaction is you leaving the channel. If you cheat, then 3 transactions need to get sent. The first transaction is you join the channel. The second transaction is you fraudulently try to leave the channel. And the third transaction is I counter you. Now, technically, in Ethereum, I'll also need to send a 4th transaction to actually finalize the payment, but you get the idea. Notice that in this case, even though in reality you have made something like 1,000 payments to me, even still, the blockchain requires 2 transactions in the best case, 4 transactions in the worst case. So why is this happening? Because the way the mechanism is designed is that it only uses blockchain transactions, first to exit the system and to enter the system, but otherwise only if there is a dispute. Only in the specific case that the 2 of us disagree about which ticket should be used are there extra transactions that get sent to the blockchain. So this is just one example. Now, there are other systems. So for example, there is a developer based in Toronto named Jeff Coleman, and you can look up his work on something called state channels, which is basically a fairly advanced generalization of this notion that goes beyond just payments. And he talks about this kind of very elaborate notion of counterfactual contracts. Contracts that do not even exist on the blockchain at all, but people treat these contracts as though they exist because if someone were to try to cheat by acting as though the contract does not exist, the person who would be negatively affected by that decision would in fact be able to submit this contract to the blockchain, and the contract would be effective. So if there was a dispute, this contract could be submitted and it would have force, knowing that if they tried to cheat, this would happen, people would not cheat, and therefore most of the time these transactions do not need to be submitted, and these contracts in reality never need to be created at all. There is also a system called the Lightning Network, which basically works by combining together networks of payment channels and basically routing payments from one person to the other through a sequence of these kinds of channels. There was also a paper released about 1 week ago called Plasma, which has made fairly big news, so I'll talk about that a bit. And it actually also uses a very similar paradigm. So the idea with Plasma basically is that you can have you can think of it as a sidechain. So it's like a separate chain from the main chain, and this separate chain is managed by some other set of validators. It could be centralized, it could be proof of stake, it could be one of many mechanisms. Now, you, as someone who has, let's say, Ether on the main chain, can send your Ether to the sidechain. Then inside of the sidechain, you can make transactions. And if you want to to withdraw your Ether, then you send another transaction on the main chain and get your Ether back. Now, normally, you can imagine many, many transactions all happening inside of the sidechain, and the main chain just never finding out about any of them. Now, let's suppose there is a dispute. What is a dispute? A dispute basically means either a sidechain block gets created which is invalid, or a sidechain block gets created with missing data. If this happens, then there is a mechanism where everyone who had coins in the sidechain before the faults took place can withdraw their coins. So only in the event that there is some fault in the sidechain, where there is some dispute, are you going to need this larger number of main chain transactions to start happening. Most of the time, there is not a dispute. And so most of the time, the main chain does not need to be used. So you can imagine these sidechains as potentially being used for many different applications. You can imagine them being used for payments. You can imagine them being used as a decentralized exchange. You can imagine them being used for general purpose computation. Anything that's parallelizable, as Joseph Poon says, anything that can be map reduced. You can imagine them being used to run potentially even as complex applications as you would run on top of Ethereum itself. Now, What are the security trade-offs of this? One of them is, if somebody wants to cheat you, they cannot cheat you, but what they can do is they can force you to wait. They can force you to wait 2 weeks to get your money back. They can force you, to send a transaction on the main chain, wait an entire challenge period, and after 2 weeks, get your money out. So people cannot steal from you, but they still can annoy you. This is the first security trade-off. The second security trade-off is a somewhat more serious one. And the security trade-off is this. Let us suppose that we have networks that everyone on Ethereum uses Plasma, Lightning networks, state channels, payment channels, for everything. Let us suppose that even if the capacity of the main Ethereum chain is 10 transactions a second, we can imagine 1 million transactions per second happening on these secondary networks. Now, let's imagine there is an attacker, and this attacker is a fairly large entity, and this large entity has some relationship with and some ability to control a large portion of all of these channel systems. Then you have a systemic risk. If this attacker attacks all of these channels, or many of these counterfactual systems at the same time, you have the problem that there is not enough space in the blockchain for everyone who is harmed by these attacks to challenge them. And so either everyone will have to be delayed pretty much forever, or some portion of these attacks is going to get through. So this, I would say, is kind of the fundamental security ceiling of these kinds of systems. And the problem is that it's, just like systemic risks in mainstream finance, it's hard to estimate. So there are a few mitigations to this. So for example, in Ethereum, you can create systems where if a channel notices that either that channel or other channel systems are currently being attacked, that it extends the challenge period. It gives more time and more block space for people to send their own challenges. And so normally, the challenge period might be a day. If a serious attack happens, the challenge period could just keep on being extended until the system knows that there was actually a day's worth of free block space during which a challenge could have been submitted. There are mitigations like this, but the ultimate and most powerful mitigation of all is to increase the scalability of the base layer itself. So how do we do this? And this is where it gets to discussing this technique that I call sharding. And the idea here is basically simple. In most networks, in even most mainstream centralized systems, you are not going to have one single computer process every single person's behavior, every single person's actions and operations. You're going to try to split the workload up among a large number of nodes, a large number of computers. Each individual computer in the system might only process a small portion of all operations. Can we apply this exact technique to the blockchain as well? Now, it turns out that blockchain sharding is harder than database sharding. And blockchain sharding is harder than database sharding for one simple reason, is that you're not in traditional database sharding, you are sharding between different computers that are still within the same administrative domain. You're sharding between in a way that's architecturally decentralized, but that is politically centralized. The same guy controls all the computers, okay? Sure, you have an Amazon data center and you've got 1,000 computers with 10,000 cores. Guess what? Jeff Bezos still runs all of them. In a blockchain, we do not want to have platforms where running a full node requires you to be Jeff Bezos, or Elon Musk, or Mark Zuckerberg, or some Chinese billionaire, if you prefer those. So you want systems where in order for a blockchain to be fully decentralized, I believe that any single role in the blockchain should be a role which is accessible to the common man. Even if a single user cannot personally verify every single transaction in the platform, you still want the entire platform to be, at least in principle, capable of being just made up of a large collection of single users. where each individual user can participate in verifying any specific set of transactions that they want. You want to have systems where there are no master nodes, there are no kings. You just want to have a kind of fluid, kind of maximally horizontal, maximally flat network. Now, in order to achieve this, just sharding between computers is not enough. You are also sharding between administrative boundaries. You are sharding between different people who do not necessarily trust each other. So why is this hard? Well, I can explain it simply in this way. Let us suppose that you have a list of 100 numbers, and you want to do the very, very hard computational problem of adding them all up. Let's say further that you are lazy. Here's what you might do. We'll do some sharding. You add the first 10 numbers. You add the next 10 numbers. You add the third 10 numbers. You add the fourth 10 numbers. Then, broadcast these 10 pieces of work to 10 people. They all reply back. And then finally, at the end, I have 10 numbers, and I then add up all those numbers, and I have my answer. MapReduce, right? Problem is, if we are sharding across administrative boundaries, then I have no idea myself that the answer that you gave is correct. If I am a node that's responsible for processing one particular set of transactions, I have no idea that just by myself that the nodes that process the other transactions did their jobs correctly. And so not only do you have to shard in a way where the work is split up, you have to shard in such a way that the work that is being split up is still checked over in a sufficiently rigorous way that even if a substantial portion of all nodes are malicious attackers, they still cannot get invalid blocks or get unavailable blocks through without the system catching it and without the system rejecting them. It turns out that this problem is hard. And if I had slides, I would have very nice slides that would explain part of why this problem is hard. But since I don't, those who are more technical can feel free to look up the sharding FAQ. Also look up the data availability problem, particularly the idea that data availability is not a uniquely attributable fault, and the fisherman's dilemma. So there are kind of very deep reasons, and also 1% attacks, not 51, 1%. So there are these kind of fairly deep reasons why in a sharded system, gaining that kind of sharding between administrative domains is actually pretty hard. So I can go brief a bit into it. So if you look at 1% attacks, for example, the idea is very simple. Let us suppose that we have a simple proof of work chain. And in this proof of work chain, every miner can choose which part of the transactions they validate. Let's say that we have 100 shards. Here's the problem. Let's say you are an attacker. You have 1% of the hash power. You concentrate your entire 1% of the hash power on one particular shard. You now have 51% of that one shard. You now have the ability to make that one shard say whatever you want it to say, even if it is incorrect. This is a kind of attack that the network needs to be able to resist and handle. This is part of why sharding is hard. To people who here now understands why scalability is hard? Who here now understands why scalability is harder if you're trying to be decentralized? Excellent. Who here doesn't understand? Okay, so there's people who understand, there's people who don't understand, and there's people who raise their hands for neither. How many of those people believe that people who do not raise their hands are the Antichrist? Cool. Okay, so that's scalability. Now, I can also move on to talk about some other problems. So one other simple major challenge that blockchain applications have is the challenge of privacy. So how do we explain the challenge of privacy? Well, you have an open public database, and this is an open public database that contains the transactions sent by each individual user in the entire system. If I send you a transaction on Ethereum, that is a transaction that is visible to every single person in the entire network. Now, for some use cases, this is actually totally fine. If I am using Leroy and I am sending decentralized tweets on Leroy, then I actually want the entire world to see them. But if I am making some kind of private financial transaction, I may not want the entire world to see the details. And so the challenge is, though, is that you could imagine, well, what if we encrypt the transaction so that only I see it and the recipient sees it? But this kind of encryption has a problem. If we create a transaction where only I see it and only the recipient can see it, then that means that only I can verify it and only the recipient can verify it. But as I said earlier, in a financial system, a transaction between A and B is not just of interest to A and B. It is also of interest to any other actor in the community that might want to receive those same units of money. So we need to find a way to give people the guarantee that you are not just printing coins out of thin air and that you are not stealing coins from other people without letting them see anything else about your transaction. Now, you may have heard of simpler techniques like mixing systems, coin join, ring signatures. So a lot of these tends to be kind of fairly lower grade forms of obfuscation. And one of the simplest forms of obfuscation is this: have many different accounts. Do not have one account from which you run all of your activity. Have lots of different accounts and try to split up your activity between different accounts as much as possible and try to preserve the property that these accounts cannot be linked to each other. This is one example of a very real privacy gain that you can make that does not require that much technology. Now, you can then go up and go up a few notches, and you can talk about things like mixing systems, where 5 people throw in their money, 5 people get their money out, but you do not know which input corresponds to which output. So only the person to whom each output belongs knows which input it came from. This is another example of a thing you can do. There is also a technology that you will hear myself and many other people talking about frequently called zero-knowledge proofs. And a zero-knowledge proof is this kind of very fancy magic piece of cryptography that basically does the following. A zero-knowledge proof lets you say, I know a number such that this number has some mathematical property, so that some function f of x equals y, without revealing anything else about what that number is. So let's say, for example, that I know a number such that that number is prime, the hash of the number is prime, the hash of the number is also prime, and so on down 10 hashes. Let's say for some reason I find such a number, and let's also suppose that for some reason you care about the fact that I know this number. I want to prove to you that I know such a number, but I do not want to give you the number, because that would not be fun. So instead, I can use a zero-knowledge proof that basically mathematically prove that such a number exists, that a number such that if you pipe the number through this mathematical function, it outputs true, exists. And I can give you this proof, and this proof will convince you of the fact that such a number exists and that I know this number, without giving you any other information about that number. Who here feels that this is something magical? Here's one example of a direct application to finance. Let us suppose we have a blockchain, and on this blockchain, everyone's balances are encrypted. Let's say then that if I want to send a transaction, the transaction is also encrypted. So that everyone's balances are encrypted, and an encrypted transaction looks as follows. Here is an encrypted version of my old balance. Here is an encrypted version of your old balance. Here is an encrypted version of my new balance. Here is an encrypted version of your new balance. And here is a zero-knowledge proof that verifies 2 things. The first thing that it verifies is that the difference between the decrypted my old balance and the decrypted my decrypted new balance is the same as the difference between your decrypted old balance and your decrypted new balance. So you are getting as much as I'm losing. The second thing that it proves is that none of the numbers are negative. So we're not creating new money out of thin air. These two are both mathematical statements. You can express both of them as a mathematical formula involving the plus sign, the minus sign, the equal sign, and the greater than or equal to sign. Anyone here dispute that? Okay. So this is clearly a mathematical property. So we can just make a zero-knowledge proof of the fact that the decrypted versions of these balances satisfy these properties and include the zero-knowledge proof along with the transaction. And so we convince the network that this transaction is not doing anything that violates the system's rules, but nobody else learns anything about the details of the transaction except for the fact that this transaction is following the rules. So to whom here does that seem magical? Welcome to the state of cryptography, at least as of 3 years ago and arguably as of 30 years ago. Who here has been inspired to become a cryptographer? Cool. Well, you should be. So, these are just all examples of different solutions to privacy challenges. And our next major updates to the Ethereum protocol, which is called Metropolis, is actually going to include quite a few of them. So it's going to include support for the kinds of cryptographic operations that you need in order to efficiently implement zero-knowledge proofs for your smart contracts. It is going to include support for cryptography that would do ring signatures, which can make mixers. And these can be used for various also things like anonymous voting. They can be used to verify correctness of transfers of various digital tokens. They can be used for lots of different use cases. So this is probably one of the major focuses of Metropolis. And aside from this, the other major focus is that it contains a number of different tweaks that all somewhat increase efficiency in their own different ways. So things like the revert opcode, which makes contracts more gas efficient. Things like the removal of intermediate state roots, which should increase Merkle tree recomputation by about 20%. None of you need to care what Merkle tree recomputation is unless you really want to, but you can still benefit from Ethereum being 10 or 20% faster. So a few things like that. Right, so this is the content of the next major change to Ethereum that we call Metropolis. After this, then after Metropolis, and by the way, Metropolis is currently at this point in the testing stage. So we're in the stage where we're finalizing writing up all the tests for all the different features, which are basically implemented in all the implementations by now. And our next step is to basically wait until all the clients are passing all the tests, and then after that, we set a release date and it's done. So that's roughly an idea of how close we are to Metropolis getting released. After Metropolis, the next step is what we call Serenity. And Serenity is, the main flagship feature of Serenity is a switch to something that we call proof of stake. How many people here are familiar with proof of work? How many people here are familiar with proof of stake? How many people here are familiar with proof of retrievability? How many people here are familiar with proof of Antichrist? Okay, so proofs of stake. The basic idea is that it's an alternative to proof of work as a form of decentralized consensus. So it's an alternative way of securing open public cryptoeconomic networks such as Ethereum. And the basic idea behind proof of stake is that instead of kind of voting with assets in the real world, so in proof of work, you can think of it as kind of nodes in the network are voting on which blocks to accept by sort of mining with, doing this process called mining with their computers. And these computers are basically representations of wealth in the real world. In proof of stake, instead, it's a kind of voting that happens with digital assets that exist inside of the system. And you can think of this as being good for two reasons. The first reason is that right now, both the Bitcoin and the Ethereum network, I believe, consume something like about as much electricity as all of Cyprus. Now, being socially conscious citizens who care about things like global warming, not putting Singapore underwater, we want to try to reduce energy consumption. And we want to try to move Ethereum over onto forms of consensus that do not consume as much electricity. So proof of stake, because it does not require kind of constantly demonstrating that you have access to physical hardware by running the physical hardware 24/7, it really cuts down on the electricity costs probably by more than 99%. Now, there are going to be some capital and efficiency costs that get added, but these are very likely much smaller. So This is the first benefit. The second benefit is that because the system is secured using rules that exist inside of the system, you now have a property that basically, we as designers of the system, and we as users who buy into the system, have the ability to design and join a system with rules that are specifically designed in order to maximize security, maximize efficiency, minimize cost. So we do not have to be at the mercy of what the laws of physics say, and instead we can kind of optimize rules to our advantage in order to improve things like the level of security, the level of fault tolerance, the ability to survive long network delays, the ability to recover from faults, and all of these different things. And in general, proof of stake does tend to open the door to lots of interesting things, such as a much stronger ability to resist and recover from 51% attacks. So if people are interested in this sort of thing, then I would recommend joining our research channels. So proof of stake is intended to be a kind of two-phase rollout, and Serenity is going to include the first phase, which moves from proof of work to hybrid proof of stake, and then after that there's going to be a second phase which moves to full proof of stake. Now, if you want to follow the progress, we also have a repo at github.com/Ethereum/Casper, where we're actively working on a prototype in Python. If you want to follow sharding, we have a repo called github.com/Ethereum/ where you can follow the proof of concept in Python. So, this is already work where it's really starting to move from just being theoretical to being practical, right? So, these are the kinds of sort of innovations and advancements that we're trying to work on a technical level in order to make the protocol maximally ready for the wave of adoption that we believe will come in 5 years if the tech is ready to handle it. Aside from this, there are also smaller problems, but these problems are also quite substantial. So one of the problems that has recently come to a lot of people's attention, and that's really been there all along, is security. Security has many different sides to it. And in general, I view the problem of security as being the problem of kind of bridging the gap between human intent and the reality of code that gets executed. So what do I mean by this? Well, one simple example of security is the security of a person's account. Who here has an Ethereum account on an unsecured computer with more than $5 million worth of assets? Don't answer that. See, if you do, you know. Now, so here's the challenge, right? If you have this kind of account, this account is any transaction that's sent from this account is verified using and signed using a cryptographic private key that sits on your computer. Number one, what happens if your computer gets hacked? Number two, what happens if your computer gets lost? Let's say instead you say, oh, well, this is too dangerous. Instead, I am going to just let someone else handle my money. Well, what happens if that somebody else decides that they are going to anonymously steal their money, all of your money that they are storing from themselves, claim that some Russian hacker did it, and then go off and have a permanent vacation in the Caribbean? So these are significant trust problems. And the kind of dilemma that we have here is that what we're trying to do is we're trying to create a digital representation of the idea of human intent to send transactions. And currently, this digital representation is a cryptographic private key. But the link between this private key and what you as the user, as a human, wants to happen with your money is only tangential. It's indirect. And so that link can get attacked, right? So the challenge here is, can we come up with mechanisms of authentication that are more robust against theft, that are more robust against loss, and that generally are more likely to correspond to doing things that you actually wanted to do and not doing things that you don't want it to do, and particularly if they have to fail in ways that inconvenience you slightly instead of failing in ways that take all your money away. So this is one example of a security challenge. Another kind of gap between intent and reality is smart contract code. So let's say we have a smart contract, and the rules of this contract say we both put in $100,000 because we are reckless that way, and we make a bet. If thing X happens, I get $200,000. If thing Y happens, you get $200,000. But let's say you made a typo, and instead the rules say if thing Y happens, anyone can claim $200,000. And let's say that we go into this bet, thing Y happens, and somebody notices this bug, and they just quickly snatch the money before you can. This is an example of a security flaw where that leads to some guy being able to take $200,000 of your money. And this security flaw exists because, once again, a vending machine is a representation of the vendor's desire to only give water to people who give them money. It is only an imperfect representation, and the representation may have errors, it may be broken. Just like that, a digital smart contract is itself only an imperfect representation of your desire to make a bet. Now, maybe you managed to write a piece of code that exactly reflects your intention. Maybe you wrote a piece of code which is actually flawless, which actually does the thing that you think it does. But maybe you made a mistake. Or maybe you participated in a smart contract written by someone else, and that someone else deliberately wrote the piece of code in a way that is misleading. It looks like it's a fair agreement. Actually, there's a backdoor and they can take all the money. These are the kinds of security challenges that we have to deal with if we want blockchain applications to reach mainstream adoption. And these are the kinds of things for which there really is no magic bullet solution. And the reason why there is no magic bullet solution is because human intent is a fundamentally complex thing, and there is no kind of mathematical way to kind of properly even define it from the point of view of inside a system that's purely mathematical and mechanical. The best that we can do is try to come up with various heuristics, various things that various techniques that try to reduce risk and that try to eliminate the worst classes of errors that you can think of. So one simple example is using the idea of redundancy. Instead of holding your money in an account where that account is controlled by one key, you can hold your money in a smart contract. The rules of the smart contract say there are 5 keys, and you need 3 of these 5 keys to take the money out. These 5 keys can then be held in 5 different places, possibly by 5 different people. If you go up from 5 keys to 7 keys, then you've just described the Ethereum Foundation wallet, which holds over $100 million of funds and which has not yet been stolen from. So, these kinds of techniques, the idea of redundancy, the idea of building systems that work unless multiple components fail at the same time, is one very practical way of reducing risk. There's an equivalent to redundancy in smart contract programming, and this includes things like formal verification and things like type systems. The idea is that you can try to write a piece of code, and you can write a piece of code in a programming language that forces you to not just specify what you want to happen, but also incidentally try to kind of specify hints about the kind of behavior that you want the program to have and the kinds of things that should be interacting with other things. If you write a program and it turns out you make a mistake, and then there's a very big possibility that one of these mechanisms is going to catch the mistake. It's going to see, oh wait, you're trying to make this thing talk to this other kind of thing which is completely different. You're trying to divide an address by a number. You're trying to multiply a hash by your birthday. That is not sensical. And so this way you can kind of automatically, by forcing people to specify this thing is supposed to be a hash, this thing is supposed to be an address, this thing is supposed to be a number, this thing is supposed to be a birthday, you can eliminate a large number of classes of bugs where people just accidentally make different things talk to the wrong things. So this is one example where you kind of over-specify. You specify what things talk to other things, then you specify what kinds of things are supposed to talk to what kinds of other things. If the two mismatch, then you show an error, and you have to figure out what the problem is. So this is one example. There's now formal verification. The idea here is you can write a program, And then you can make mathematical claims about properties that the program is supposed to have. Then you can use a computer program to verify the fact that with all possible executions of the smart contract, all of these mathematical properties are correct, that all of these claims hold. So once again, you use redundancy. You specify the behavior, then you specify things that you expect about the behavior. If the behavior and the things that you expect about the behavior do not match up, then try again. Right? So redundancy is this kind of very fundamental technique that really works well across a large number of different domains. If you want to really know what someone is thinking, make them say it in 5 to 10 different ways, where those different ways come at the problem from completely different angles, and see if all of them converge at the same point. If they do not, then you've made a mistake, and you can detect the mistake, and you can give the guy a chance to correct the mistake. So these are the kinds of things that need to really be integrated into Ethereum development tools, Ethereum user tools, and made much more accessible if we want regular people to be storing $5 million of crypto tokens. So, this is another example of a major challenge. Now, there are also smaller challenges. Solving the latency problem. What if somebody wants to play StarCraft on the blockchain? How many people here who played StarCraft would be okay playing StarCraft with a 14-second latency? 1.4 second latency. 0.14 second latency. 0.014 second latency. Wow, not many StarCraft people. But even still, you get the point. There are going to be some applications where you need speed. Payments. How many people here who are merchants would really love to see their latency go down from 14 seconds to 1.4 seconds? Not many merchants here, but lots of hands. So, reducing latency is good, right? So the question is, how can we effectively reduce the latency of blockchain-based applications where that needs to happen, while making as few sacrifices to efficiency and security as possible? This is one of the problems that needs to be solved. And this is an example of problems that we're working on. How many people here are interested in helping us work on any of these problems? At least some. So, if anyone is interested, then I would actually make a few recommendations. So first of all, we do have public Gitter channels. So if you go to gitter.im/Ethereum/research, or even if you look at just start poking into the Ethereum research wiki and some of our other Gitter channels, then you can start talking to some of our developers and starts to get an idea of the kinds of things we're working on, the kinds of problems that we're thinking of. Over the next couple of months, we're probably going to very substantially expand the kinds of ways that we kind of interact with the outside research community. So, keep your eyes open, and hopefully at least some people will look forward to that. So, getting blockchain technology from the point where it is now to the point where it can really be used by the masses really is something that requires all of us to work together. And, hopefully we will see more people interested in kind of putting in their talents. And if anyone wishes to help, then we're happy to work with them. So aside from this, there's also quite a lot of challenges that exist at the levels of each individual application itself. If you're building a payment system or a financial derivative system, you're going to have your own security challenges that might not necessarily be the same as the security challenges of other applications. These are also things that need to improve. Another major one is the links between the blockchain world and the outside world. Gold is currently not traded on the blockchain. Has Digix launched yet? No.
End of August.
Okay, end of August. So, pretty soon gold will be traded on the blockchain. There you go. Link between the blockchain world and assets and assets that are normally traded in traditional finance. Information from the outside world getting put into the blockchain. Information like prices, weather, real-world identity information. All these feeds from IoT devices. Any kind of thing that applications on the blockchain could benefit from that comes from the real world. We need more links. So there's still quite a lot of challenges that do need to be worked on. So this is kind of roughly where we are probably at with Ethereum's progress from a kind of very broad perspective. Now, there are also obviously challenges that exist inside of each individual project. So, for example, people might want to know about platforms like Whisper and Swarm. So these are kind of sister protocols to Ethereum, and you can think of them as decentralized messaging networks that do not have memory. So if you want to send someone a message, and you're okay with that message not being stored on a public ledger forever, but you want to make this message arrive faster, be cheaper, not pay transaction fees, then you'd be recommended to use one of these two networks to use it. If you want to store a file that would be used by decentralized applications, you could do this on Swarm. So these are also both systems that are currently in alpha stage and that are progressing kind of forward, I would say fairly quickly. So those are two examples. Aside from this, there's also programming languages. So many people have heard of Solidity. There's also been work on a language called Bamboo by Yoichi, which is a kind of more functional style language. And there's something called Viper, which is originally developed by myself, but now has more and more outside contributors, thank you, which is focusing more on kind of, you can think of it as security through simplicity. So there's a lot of other smaller projects that are also happening as well, but there's probably too many to fully talk about right now. So do people have any questions?
So before questions, let's give Vitalik a round of applause.
No.
Okay, so we can take questions for about 10 minutes. I'll be just asking, yes. Please stand and ask the question, yeah.
Okay.
So the question is, Ian, right? Ian is asking, could you please talk a little bit about Polkadot and the differences between Plasma?
Sure. So Polkadot is a network that is specializing mostly in kind of blockchain interoperability and cross-blockchain transactions, including transactions between existing networks, but also offering the option for networks to kind of build themselves on top of Polkadot and gain some of the benefits of its security. And Polkadot is an independent blockchain, and it's going to have an independent token, and the token is going to have a sale. Plasma is a way for people to build their own networks, which are basically sidechains of Ethereum, and where the security of the networks is ultimately guaranteed by the existence of enforcement mechanisms based on top of Ethereum itself. So Plasma is in kind of collaboration between Joseph Poon, who is also financed by the Omise Go team, some of whom are here on the left, and as well as some work by myself and a couple of other development teams that should be announcing themselves at some point soon.
All right.
So the important thing about Plasma is that Plasma is not like a single thing. It is a protocol that anyone can use to build their own thing. And so if you want to build a Plasma network, anyone can do this. They do not need to kind of connect to any kind of specific vPlasma thing. They do not need anyone's permission. You can just do it.
Yes, thank you.
In regards to the fundamentals, you didn't address the question of breakability.
Of what?
Breakability.
Breakability.
And one thing about it, in reference to that, with your regard to this fact, because you did not include your t-shirt as a basis of contradiction when you say that the DNS, whether version 4 or within IPv6, no, the question here is that originality versus counterfeit.
Yes.
You say that here, do you contradict your own principle with that?
Oh, how do I contradict my own principles? I'm confused.
It's up to you to choose to answer.
Yeah, I'm not sure if
No,
Okay.
the hard forks.
hard forks. I think in general, hard forks are a necessary way to kind of improve and upgrade protocols, and especially when a protocol is still in rapid development, you're going to see lots of hard forks happen. And as a system becomes more mature, obviously the number of them will decrease and they'll become more conservative, but like in general, protocols do need to improve, and that's just my own view.
Thank you. Yes, gentleman back. Let me repeat it. Right, so the question's on regulation. He's asking a legal question. He's asking, should regulation be in the space, and how do you see it going forward?
Yeah, so I think that as the industry becomes more mainstream, there's definitely going to be more interest in regulating it from all different sides. I think one of the just important things that I hope regulators keep in mind is basically that the kinds of concerns that are going to arise inside of this system are not necessarily the same concerns as the kind of concerns that existed in previous industries. So for example, here it's not so with these kinds of systems, the kinds of concerns that you see are not so much, is this particular person trustworthy? Is this particular person someone who's likely to cheat you? But more things like, is this piece of software broken? Is this particular protocol reliable? The kinds of issues that are in this space are, very substantially different from a lot of the kinds of issues that existed in previous spaces. And so, if you try to too quickly take existing approaches and try to kind of force them on top of new systems, then either you're going to end up with rules that don't do anything, or you're going to end up with rules that are actually counterproductive because they basically forbid people from doing the kind of obvious simple thing and instead require people to do these kind of weird, complex workarounds that are actually economically equivalent to the simple thing, but try to kind of wave around it to avoid being put into regulated categories. Or you push too hard and just end up shutting the whole thing down. So it's I think it is definitely a delicate challenge, and I actually do think that both the MAS in Singapore and many other regulators around the world have shown quite a bit of very healthy restraint that I do have to applaud them for.
Yeah, I think if I try to keep regulation and any other related questions out, just try to keep the questions going on the tech itself. No. Yeah, so the gentleman back there, yes. You, yeah.
So as you're developing this infrastructure that stands to impact lots of people, lots of different communities all over the world, do you have any plans for ways to have the developer community become more diverse? I don't know that much about it, but it seems like a lot of dudes.
Right, so his question is, as it becomes more popular, are there any ways to introduce diversity into the tech? Just a quick answer on this.
Yeah, so I think diversity is, first of all, it's something that you can't really force, and if you try too hard to force it, then you are going to just basically cajole a bunch of people who are not really interested. So I think the important thing, especially at the early stages, is first of all to make sure that you're reaching out to diverse communities. And this is something that we try to do. So for example, we reach out to groups like this meetup, we reach out to academic groups, we reach out to kind of business audiences, various companies, governments, and we do try to bring interest from these lots of different perspectives, also going all the way up from just the university students to professors. Another thing is one of the reasons why I think Ethereum as a system is capable of being diverse is because it's not just about money. So it's a system that's designed to be usable for many different types of applications. And one thing that I think we can continue to do is to try to basically emphasize this and focus not just on one particular industry, but on this idea that this is a system that really can be used by people as diverse as enthusiasts building prediction markets, the UN World Food Program, people building payments interoperability platforms, and people speculating on ERC20 tokens. And the fact that this is a system where all these different diverse groups can benefit, I think, is something that we should kind of continue to strengthen.
Sure, thank you. Yes, gentlemen. Sorry. Yes?
Thanks. We launched tokenized Apple shares on La Token Ethereum platform, and we are expecting to add about 10,000 equities and debt tokenized. And there will be 1,000 transactions per second. So what do you think? When Ethereum will be capable to support this?
So I would recommend that if you are building an application that will need to support thousands of transactions a second, for now, either put it on an Ethereum-based consortium chain. So for example, there's a company in Taiwan called AMI that released a consortium chain version of Geth that can do about 500 transactions a second a month ago. Or in the slightly longer term, build a system on top of Plasma. And in the longer term, hopefully, like Ethereum itself will become will become sharded, and the public chain will be able to support a much higher load. And when that happens, then you can do Plasma on top of that and get even more scalability.
Okay, sorry, Omisi, Thomas here wants to say something about. No.
No, just about Plasma. Yeah, no, I wasn't looking for a shout out. I just wanted to I wanted someone to clarify that Plasma is not exactly a sidechain.
That Plasma is not
what? Exactly a sidechain.
Right. I mean, it's like
not a federated sidechain.
Correct.
Which
so
is
yes,
what people normally think of.
Right.
Sidechain.
No. So the security model of Plasma, once again, is that if Plasma chains can be either consortium chains or proof of stake chains or one of many mechanisms, and the security model is that you do not have to fully trust the mechanism that's running the Chow chain. If the Chow chain works fine, everything works great. If the Chow chain consensus breaks, then the attack on the Chow chain can delay everyone getting their money out by 2 weeks, but it cannot cause people to lose their money unless there is this really, really huge amount of usage and you have this kind of systemic risk attack. But we're still, I would say, fairly far away from that.
Sorry, okay, I guess we don't have much time for questions. If any other questions, please reach out to the channels that he mentioned earlier on. Get onto the Gitter channels, ask him. And before I close off, I'd just like to encourage you guys that this whole meetup was set up for a community purpose. So go around, talk to startups around here. We have guys from 10x at the top. Give a shout out. Yeah, we have my DJ's crew. My DJ's team is right all the way at the back. We have Swipe Crypto somewhere around here. There's a lot of other startups around here that are always coming by, create that diversity that people talk about. So I believe that this kind of meetups are all generated to create conversations, not just with the founder, of course, themselves, but among yourselves. We all want to be here to create ideas and to make ideas a reality. So before we conclude, I'd like to invite Shiha from SG Innovate to give a short talk about the event.
Thank you, Sean. Thank you, Vitalik. Good evening, everybody, and welcome to SG Innovate once again. And thank you very much for coming. So I'm going to make it quick tonight. So what's happening is this conference that's coming up called Switch, Singapore's Week of Innovation and Technology, and we encourage people to come together, startups and all. So our aim at Switch is to connect with the brightest, boldest, creative minds, deep tech startups around. And I'm inviting all of you to come down at Marina Bay Sands just after the F1 weekend, 18th to 20th September. I hope to see all of you there, and feel free to approach me for any questions, queries, exhibition, booths, or anything. So thank you once again. Thanks, Sean.
Last word.
By the way, does anyone remember who the company was that sponsored, that showed up as a sponsor at the beginning of the meetup?
Yes, I believe there was one. Yeah.
What was the name?
The organizer name is Arifa.
Oh, okay.
Yeah, that's all I know.
Okay.
Yeah.
So special thanks to both Arifa and Switch for taking the high road and showing their posters at the meetup with the permission of the organizers and by actually being sponsors.
I'll just clarify that the organizers does not include them.
Okay.
Sorry about it.
Still.
Yeah. Okay. So let me take this opportunity to thank a couple group of people that I really want to thank. Firstly, I'd like to go out these two gentlemen here, Ernest and Taufik. They have been working all afternoon with us just to get the whole footage done properly and just to hype up the whole event. The F&B sponsors, French Cellar, I believe they're on level 4. Okay, so right now the food is a bit mixed up right now. Food is at the back, wine is upstairs. So apparently you eat your fill and you go out for your own fun. French Cellar, who actually supported the previous Kyber Network meetup, they are promoting their wine club special discounts on wine bottles of more than 20 pieces. And they have a special exclusive membership only available for tonight. Secondly, the food is proudly sponsored by CoinHarko. Anyone here knows who CoinHarko is? You guys know, right? CoinHarko is probably the biggest Singapore and Malaysian exchange, crypto exchange, and you definitely know what they do. And lastly, I'd like to thank SG Innovate very much for providing this support here. I hope to see you guys at the next event, which is next week on 22nd of August by Ethereum Foundation. My name is Sean. Thank you. Good night. Guys, there's something on at level 4, so I hope you guys can just hang out for the wine. It's sponsored. Please help me finish them. We're going to carry all of them back. Thank you.